this is joint work, as you said, with Daniel, who's in the audience. And it's a very simple stochastic spatial model about, I think, a basic process in evolution and adaptation more specifically. So when you have adaptation by new beneficial mutations, then what you need to have is that a new mutation that's initially rare becomes frequent. Okay. And it's an important question to ask, how fast is that process? Because there are many regimes where this time, where an initially rare variant becomes very frequent, dominates or controls how fast adaptation occurs. And when we think about this process, normally in population genetics, we think, okay, a new variant which is unconditionally beneficial, it will spread exponentially. But when we do that, then we have the assumption that more or less the population is well mixed. Every individual interacts with every other individual, and then naturally you get exponential growth that then saturates after some time. But when you have space, when space is important and you have limited dispersal, then you slow down. And this talks about how quickly you slow down. When you have long-range dispersal, there's a very important regime which has been understood quite well. That is when you have only local dispersal, so meaning that sort of your dispersal kernel is, for instance, Gaussian. You only jump to your neighboring sites or not very far away, and then you get traveling waves. But this is about exploring other regimes that come about when you have broader dispersal kernels. Okay, so the basic process I have in mind is illustrated here. So imagine you have a resident population, which is this blue one, and then a new type appears, which is more reactive, reproducing faster, and then it's clear if it survives the initial phase, the initial phase where the mutant or this variant has to struggle with fluctuations, genetic drift, to even establish. When that has occurred, then it will just deterministically spread across space. It's a supercritical process I'm considering here. And the question is, how fast is that? So I think the initial phase, establishment of beneficial mutations is also very interesting, and there's still many things to explore actually in spatial systems, but I'm only going to talk about essentially this later stage where you then have established and the game is to expand in the population. And that occurs in many contexts. So I've just framed the problem in thinking about spreading of an advantageous mutation, and that has been started by Ronald Fisher, Kolmogorov, and PP, Piskunov, and the last P, I forgot. Huh? Pitofsky, exactly. So, and they did this in 1937. I will mention that model later, and many work has followed up on that. And there in the audience, people, obviously, that have thought a lot about this as well, this particular process, and most of these other spatial processes as well, which are in a way equivalent. There are new twists that come into the problem. So for instance, if you think about epidemics, the spread of infectious diseases, then what this process here corresponds to is an SI model, where you have a susceptible type and an infected type that comes in. And then essentially you have a chemical reaction where S plus I has the tendency to go to 2I. The reverse, S plus I can also go to 2S, but this is sort of more likely, and then you get spreading of the I type. And in epidemics, you have to think about other more complicated models as well, where you have also the process where infected goes to recovered, and I will touch on that in the last couple of slides as well. But for now, let's focus on the simplest kind of epidemic reaction, epidemic spread that can occur. Also, this process essentially happens when you have the spread of an invasive species that is introduced into some virgin territory, and then the S type essentially is empty space that gets displaced by the invasive species. Also, you can imagine spread of information, gossip, and also there a number of people in the audience have worked on that, or at least at UC Berkeley. What? Tom Aldous, for instance, has worked on that. So the question I'm going to ask is, how fast is that process in the presence of long-range dispersal. So let's first think about this epidemic scenario and look at how it happened in the past. So this is a reconstructed map of how the bubonic plague spread in the 14th century from the south of Europe to the north. And from this reconstruction based on historical record, it looks like, okay, it spread more or less wave-like, and it rather slowly. So it took like, it advanced on the order of 300 to 600 kilometers per year. Compare that with, for instance, the spread of SARS in 2000, I think, 2, right? It emerged in a province in China, and then first spread locally, but until it more or less infected a person that went on the plane and moved to other places. And then it spread very quickly across the globe. And it spread essentially within 6 months to many places across the world. So what's the big difference between these two scenarios? It's of course different diseases, but it's likely that the dispersal mechanism is what makes a big difference. So in the past, what you could do is you could walk, or you could take a horse. You could also take a ship, and then you can move away still further, which shows you that really long-range dispersal can be rarely excluded. But today it's more evident. Oh, this is very pixelized, this image. It's in reality much more beautiful. This depicts the avian transport network, so of airplanes across the world, and they're supposed to, you should be able, so in the better picture, you would be able to see like big circles for big airports and thick lines for strong connections. But what you still see that, there are lots of connections and long distance connections in particular. And this leads to dispersal that is long range. Okay, it's very hard to measure really precisely how humans move across the globe. But what has been done, for instance, is a study where people tracked the traveling of dollar bills in the US. So you might have seen single dollar bills which have on them a stamp essentially saying, where's George? Okay, and then a number, okay? And when you see that, you can in principle go online to a website and record that number and the place where you found the dollar bill. And on that website, they're essentially storing that information. And originally, it was just a hobby of a couple of people that started this, until essentially one study realized this is a great resource of information which you can use to study essentially how dollar bills at least travel across the US, and from that perhaps infer how humans are actually moving. So at least in the case of dollar bills, what they found is that they disperse according to a distribution which has a broad tail. So P of R here is the range over which a single dollar bill travels in a fixed amount of time. The time they chose for this plot was 4 days, I think. And you see on this double log plot that it has a broad tail. So it seems to have a power law tail, at least over 2 orders of magnitude, with an exponent minus 1.6. So the question I want to raise in a very simple model is, how can we explain the qualitative difference between these two scenarios here and the ensuing epidemic evolutionary spread?
Sorry, Oskar, what does the inset picture?
I think here they chose a different time of spread.
Yeah.
And just to show that essentially they get the same exponent. So let me anticipate very simple simulations that I show you more of later on, where I essentially have a 2-dimensional lattice, and in the center there's a little dot, so it's seeded by just one occupied site. And then all the simulation does is it randomly, in each time step, it randomly selects a source site, then draws from a dispersal kernel a jump distance, and selects a target site. And if the source site is occupied and the target site not, then the target site becomes filled. And that's continued over and over again. And on the left, and for both simulations, I choose dispersal kernels which have a broad tail, a power law tail. But on the left, the tail is relatively steep, and on the right, it's relatively broad, so that you will see a qualitative difference there. So let me start the left movie. So as the population grows, you see it's very, very noisy, and you get longer range jumps. But if this grows further, then after a long time, and if you look at large distances, it really just looks like a growing pancake that grows essentially at a constant speed. It's still pretty noisy there, but coarse-grained, this becomes asymptotically a circle. But it's going to be very different here on the right. So again, little circle in the beginning, but then suddenly everywhere clusters appear and grow and merge. And this looks like, we call it metastatic growth, like everywhere clusters merge, and that of course speeds up the overall growth of the occupied regions, and they are merging ultimately. And the game that we have to understand ultimately is really how these new clusters appear and merge together to understand this overall growth.
Is the density 1 first?
Yes, exactly. It's in this simple model, it's just 1. It's like more or less a contact process with long-range jumps. And before I go into this, let me just go back in time a little bit and describe in just one dimension how you might model the spread in the case where you have just short-range dispersal. And that was pioneered by, as I said, Fisher, Kolmogorov, and Pipi. And they modeled essentially the spread of a population of beneficial mutations in the continuum limit by a density C of space x and time t. And they argued that the rate of change of, sorry, it's not yet noisy, it's just a traveling wave at this point, deterministically. So they argued that the rate of change of this density profile should be given by two terms. One is essentially diffusion, so this is the second derivative of the density with respect to space, and a second term which describes local logistic growth. So when the density is small, you grow exponentially at a rate r, but then when the density approaches a limiting value, then the growth term disappears and you only have diffusion. So that's occurring here in the saturated region. And okay, this simple model gives rise to traveling waves that travel at a constant speed asymptotically, and the speed can be even calculated exactly by focusing on the tip of this wave. And already from dimensional analysis, you can see that the only way you can get a speed from these two parameters, diffusion constant, which is the length squared over time, and the growth rate r, which is 1 over time, is by forming this combination. And then, okay, you have this factor of 2 in front. And then 70 years later, it was realized, or at least the importance was realized, that really particles are discrete, typically in many applications. And that introduces an important noise term in the continuum limit, which can have different forms, but you always have this piece that the noise term is proportional to the square root of the density, and eta is a space-time dependent Gaussian noise term here. This noise term essentially represents genetic drift, which is very crucial here in the tip of the wave and really affects the behavior of the whole wave. And the reason for that is that the wave is really pulled forward by the dynamics that's going on here in these founder cells. And in the founders, the total number of founder cells is always, in a sense, small, even if the carrying capacity is very large. So this noise term is hardly ever negligible, and it was shown that it leads to a very strong correction to this traveling wave speed which scales in this form. So K here is the carrying capacity, it's the maximum density of the population here in the bulk of the wave. And you cannot get this term, for instance, by a perturbation analysis if you assume this is a small perturbation. You cannot get this term, it's a singular perturbation. So it's important here, this kind of noise. And now you might wonder, okay, can we in this framework go on, perhaps, to discuss what happens when we have long-range dispersal? Okay, a natural modification would be to replace this diffusion term by an integral term, which essentially sums up all the influx to X from other places due to jumps. Okay, and the jumps that we are going to describe the jumps by a function g of a vector, and that describes the probability density of obtaining a jump of a certain distance in a certain direction. So this is a vector here. But then the problem becomes even harder, and most of the approaches to this point have simply neglected then this noise term and assumed for a particular reason that the dispersal kernel has a power law form of this type. First of all, we will also make this convention that we say, okay, this dispersal kernel has a tail that scales like distance to the power of minus and then mu plus dimension we're talking about. If you choose this parametrization, then the dispersal kernel will be normalizable if mu is larger than 0, and the variance will be finite as long as mu is larger than 2. Okay. And many people thought in the past, okay, new behavior only appears when this exponent mu, when the variance becomes infinite. So they focus on the case, most of them focus on the case mu smaller than 2, and they invariably found exponential growth of the total population as soon as you have these long distance jumps. There was another approach which used ad hoc approximation that works in the case of short-range dispersal. And that is the approach to assume, okay, we can effectively describe the effect of noise by using a deterministic equation which has a cutoff where the growth term has a cutoff when the density becomes smaller than a certain limiting density. Then we add a cutoff which essentially makes this growth term disappear, heuristically arguing that, okay, out there are no individuals anymore.
So didn't Mollison look at this in the 70s?
Mollison is an important one who looked into the who looked at this question and asked the question, okay, when will dispersal become very important? And he found that in 1D, when you have a dispersal kernel that's broader than or as broad as an exponentially decaying distribution, you get exponential growth. So also consistent with these results. But what these simulations very quickly show is that if you neglect noise, that doesn't then you're not even close to the simulation results. And the reason is simply that these mean field approaches, in a way, they neglect the discreteness of the long-range jumps. And let me first show simulation results, and then I try to give you a flavor of a very simple argument that essentially reproduces the behaviors that we see in the simulations. Okay, I essentially explained the simulations already, and let me just do it again. So we have a two-dimensional lattice. In 2 dimensions, we focus on a square lattice. We start with one occupied site, and then we draw repeatedly source and target sites. The distance is drawn from this dispersal distribution, and then we just keep going. And the dispersal kernel that we choose has a power law tail with an exponent parametrized in this way. And that illustration here doesn't really add much. It just says that the short-range part of the dispersal kernel will give rise in the space-time plot to more or less cone-like structure, but then from these more rare long-range jumps, you get new seeds, new clusters emerging that then merge. But let me just show you now directly simulations with 3 exponents, and all these 3 simulations will illustrate 3 different regimes that occur. So this is the case where the dispersal range, the dispersal kernel is rather steep, and it will give rise to a growing pancake. Here, the variance diverges in 2D, and we get a very fast growth, which I called metastatic in the past. And here, we also get something which is much faster than linear growth, but notice the variance of the dispersal kernel is still finite in this regime. So let me start all of them together. So this one finishes first. The simulation stops, I think, when 70% of the lattice is filled. And then here, second one, you clearly see it's not anymore. It looks like a growing circle at all. And here we have much slower growth. We can analyze these simulations very simply by defining something like an effective radius. So essentially just what we do here is we take the total number of occupied sites and take essentially the square root of that to get an effective radius. And you see how it's growing here on a linear scale. The slowest growth here seems to be consistent asymptotically with the linear growth. And I show you much larger scale simulations later on that really are consistent with that. On a log-log scale, really just for that simulation that I've shown you here, you see that the 2 lower ones seem to be approaching straight lines. But the middle one here has a higher exponent. So that's indeed what we will find, a power law, a superlinear power law in that regime. And on a semi-logarithmic plot where the y-axis is logarithmic, but here's just time, you see that even the fastest growing case, the blue line here, does not seem to approach a straight line. Okay? And indeed what we find is this is described by a stretched exponential, so where the logarithm of the total occupied area grows like a power law with an exponent smaller than 1. And now let me give you a very simple argument that will result in an approximation that reproduces these simulation results, at least to leading order. So let's look at this occupied region that's generated by this process in a space-time plot. Okay, space is on the x-axis and time on the y-axis. And I'm assuming here that essentially the occupied region grows like this funnel here. So the boundaries of the funnel are not straight, because I'm assuming now that the occupancy grows faster than linear. So it has to be bent in this way, and this bend is very important. And what I'm also assuming in this illustration, one can do better than that, but what I'm assuming here is essentially you have one fully occupied core, and then outside surely there will be some density, but in this plot, in this illustration, I'm neglecting it for now. And then let's ask what happens if you have out of this funnel a long-range jump, for instance, this one here. If you have a jump that occurs and that is successful, so the seed survives essentially genetic drift, in our simulation it always does, then in this approximation we say what we should do is we should copy and paste this funnel to the point where we jumped. If you do this in this case, then you see that this emerging funnel here will contain this gray circle here. So that's the gray circle here. It plays an important role for the argument. That's at point t, that's the typical radius of the occupied region. Okay, and now I want to make an argument that gives me a relation for, or condition for this typical radius at time t. Okay, so and this argument thinks about, okay, by which ways can I get this gray circle occupied? This is just one way. I can get a long-range jump relatively late on, a seed here, and then I have to copy and paste this funnel there, and it will contain the gray circle. Gray circle is occupied, that's fine. Another possibility is a very long jump very early on, and the funnel will contain the gray circle. or this situation here. All of these three ways are individually have a very low probability. But what we are interested in is all the ways you can get the gray circle to be colonized. And if you think about that, then you find the condition that you must have is that you get a jump from this red region, which we call source area, into this blue area that's depicted there. And this blue area turns out geometrically to have exactly the same shape as this red funnel. It's only flipped around the horizontal. And it's very easy to see that this must be the correct shape by this copy and paste process. So take this funnel, for instance, and copy it to directly this boundary here, and then draw the funnel there, and it precisely cut through the gray circle because of symmetry, essentially. And that symmetry is also important for the argument, as I will show in a second. And now this self-consistency argument is simply to say, okay, if this assumed growth of the funnel is more or less correct, then what we must have is that the total probability to get a jump from the source area to the target area should be of order 1. Okay, that's the argument. Because if this total probability would be much larger than 1, then we would say, okay, then the assumed funnel shape must be faster growing because you get these jumps much more quickly. If the total probability is much smaller than 1, you would say, well, then the assumed shape was too large. Okay, and the argument can be formulated mathematically very easily. You just have to calculate this probability and set it to be 1. So the total probability to jump from red to blue, to calculate that, I need an integral over time from 0 to t, and then 2 space integrals. One is over the red region, that's the first one, and another one over the blue region. And then I have to integrate over the probability density to get the associated jumps. So that's where the jump kernel occurs. And this gives you one condition for each time t, and it really constrains the dynamics of the whole growth process, except for the initial conditions, for which you need then really the short-range part of the growth. But still, it's an integral equation, hard to solve in general. But when these funnels are growing very, very quickly, there's an additional effect that helps you, namely that most of the crucial jumps will actually occur pretty much exactly at half time. Which is another way of saying this is that this time integral here has a very pronounced peak at t half when the funnel grows very, very rapidly. The reason is simply that on short times, it's the source funnel that is very small, and therefore getting jumps at all is very rare. And at large time, it's the target funnel where you have to jump into. It's very small. And because the integrand here is essentially a product of total occupied mass and total target area, what you get is ultimately a pronounced peak, and by symmetry it has to be a t half. So what you can do is a saddle point approximation. So this equation now gets in this limit where you have very fast growth. It gets to be replaced by this much simpler expression. And you can directly interpret this product on the right. Again, it's supposed to represent the total probability of getting a jump from the red region to the blue region. And we are carrying out a saddle point approximation, so meaning that the crucial jumps happen at t half. So you need to essentially I multiply here the size of the source region at t half, which is L of t half, to the power of the dimension, with the total area of the target region at the same time, which is the same. Okay, so we just get L of t half to the power of 2d for this product. We have to multiply it for the probability to get a jump by what distance? The distance of typically L of t. And we have to multiply, we need another time factor in the front from the saddle point approximation. And now, if we now we don't have to choose a power law distribution for this kernel, but it's convenient to classify the behaviors, and that's what we're doing now. So if we insert for this dispersal kernel a power law, which is as I described before, then we end up with this very simple recurrence relation of L of time t in terms of L at time t half. Okay, that's the argument. And this, in fact, can be solved exactly. Any questions about the argument at this point? Because now I'm going to results. So for the results, let's first look at the solution to this equation in the limit of very large times, essentially the asymptotics, because there actually rigorous results exist. So there are many regimes. So these rigorous results have been proven by Marek Biskup in 2004 and very recently by Chatterjee and Dai in last year. It's on the archive. So let me go through these asymptotics case by case. So let's start in the regime where this exponent mu is smaller than d. This is the fastest growth regime. There you find that the log of the diameter, the effective diameter, grows like a power law with an exponent given by this expression there. That and a prefactor b mu that we get out of this argument. The behavior here, the power law behavior, also appears in supercritical long-range percolation and with the same exponent. And the model by Chatterjee and Dai really is framed differently, but it really maps onto our epidemic model as well. And they could also prove that this is the correct asymptotic, that power law. But the prefactor is actually important because it turns out as you move towards the boundary, it's going to diverge, which signals a very slow crossover, which I'm talking about later. Yes?
So you talked originally about the power law when mu was less than 2, and you used the intuition that variance was infinite, but now you seem to have sort of switched. It seems like that was just...
It turns out that this is not a crucial distinction, whether variance is finite or infinite. That was just something people assumed from thinking about random walks, just random walks without reaction. But when you have reaction and random walks, it doesn't matter. It's different conditions that matter.
There's nothing special about the
And am I right that that was partly because they happened to be doing all their simulations in 2 dimensions? Right? Because before you were talking about mu is less than 2, and now you're talking about mu is less than d.
No. So in any dimensions, when you have in the parameterization you choose, when mu is smaller than 2, the variance is going to be infinite.
Right.
They thought about any dimension, but I guess they did simulations in 1D mainly. Okay, then if the exponent mu is between d and d plus 1, you get power law growth with an exponent given by this expression. And again, the asymptotic exponent power law is proven by Chatterjee and Dai, a really very nice work. And but again, the prefactor is important. It diverges at both boundaries. And for mu larger than d plus 2, you get indeed just linear growth with a speed that's going to be dependent. Should have written that there. Also on the exponent, and the speed is going to diverge as you approach the boundary there. But then, turns out very importantly, are actually the marginal cases when mu is exactly equal to d, then you get a growth where the log of the diameter grows like log squared of time. So very funny functional form here with an, again, important prefactor, which depends on the dimension. And here at the other boundary, the diameter grows like t log t. Now, these are the asymptotics. They describe the behavior at very long times. But it turns out at finite times, the behavior looks a little bit different. So I'm plotting this here for the behavior essentially as a function of this exponent mu. And I'm choosing here a variable delta, which essentially measures how far is mu from d. Okay, so mu equals to d is precisely a boundary between stretch exponential and superlinear growth in the limit where t goes to infinity. Okay, that's what I described before. That's the asymptotics. But in the at asymptotic times, the marginal case really just matters at mu exactly equal to d. But it turns out that for finite times, the marginal case blows up and represents a very important intermediate asymptotic case. So if you start here, for instance, and run your dynamics, at first you're just deep in the marginal case, and then cross over to the superlinear growth. And actually, the relaxation time is very, very large. So the log of this relaxation time goes like 2d divided by this parameter delta. And it turns out that, for instance, if delta is less than 0.3, it is essentially impossible to get out of the marginal case in simulations, and even more so in nature. So in nature, so you essentially, by the time you get out of the marginal case, then your system or your occupied region is so large, larger than 10 to the 9, that it cannot matter, at least on Earth. You know. Perhaps in the world still, but yeah, so it's really important then to have a fully dynamical equation that describes the growth of this occupied region, and that is shown here. So this is essentially the solution to that recurrence relation that I introduced before. It describes, it's a simple equation for the log size of this effective diameter in terms of the log time that has elapsed, and it's given by that expression. And it entails these different regimes asymptotically that I described to you, but also the dynamics here. And we can test it by running simulations. And of course, I can prove we did simulations in 1 and 2D, and both agree pretty well. But in 1D, of course, I can get to much larger systems by the simulations I described. So here you see the simulations on a semi-logarithmic plot. And the exponents I chose was 0.6, 0.7, 0.8, 0.9. 1 would be exactly the marginal case. Don't know why I left it out here. And then 1.1 and so on to 1.4. And it agrees pretty well with the data. So I plotted here individual runs. For each case, 10 individual runs. And so you get some spread here, but the predictions lie pretty nicely on top of each other. But on a double log scale, you see, for instance, that for these cases here, okay, let's look at these blue lines. So what do they mean? For these cases here, asymptotically, we expect a power law with a particular exponent. Power law in a double log plot looks like a straight line. And for these cases, I indicated the asymptotic exponent by these blue lines here. Okay. And you see that for this case, for instance, which is 1.1, even though we have simulated up to 10 to the 7, roughly, we are not even close to this asymptotic power law regime. So,
are you looking at the furthest particle from the origin, or where there's a positive density?
So this is just the total mass of the population. This is also an interesting question to what differs. You know, these are further questions. I'm not talking about these.
To get the furthest one is simple argument to get so close.
Yeah. And there's a much better test, which I don't show here, actually, which applies. So a test for the theory. The best test for this theory, for this argument at least, is when you are very close to the marginal case, because then this function here collapses onto a scaling form, where you can essentially plot data from different exponents in one plot, and the different data will essentially map out different effective times in that plot. And then the prediction would be that they all collapse on one curve, and that's indeed the case. And you can look at the preprint if you want to see that. I can also, if you're interested, show that in the question section. How much time do I have? We started a bit late, right?
Yeah.
Or early?
Say 5 more minutes.
5 more minutes, okay. So let me get quickly. This is just a summary of what we had. You can, by extending the argument, you can also describe the density profile, so not just a core, which is essentially 1 and then assumes it's more or less 0, but you can describe the density outside this core, the expectation for that. And you have here a couple of nice plots in 3D. But let me just mention further things that need to be done or should be done. So far I just looked at the SI model, but you can easily imagine what happens if you now have, in this epidemic framework, also recovered individuals. Then you have a process where I goes to R. Okay? And then what you effectively do, you burn a cone of recovered individuals in the source funnel, which changes the geometric picture. It's not anymore the case that you have these totally identical areas, and the saddle point approximation, you can still do a saddle point approximation, but you don't have this exact symmetry anymore. And then this particular case asymptotically really maps onto what was described by Marek Biskup, onto supercritical long-range percolation, and also in simulation. And this has been shown to work very nicely by Grasberger recently. But what this argument that we present does in addition is that you can now describe the crossover from initial, where you have just an SI model, to the SIR model and get important prefactors out. In principle, I think there's no way, no obstacle of extending this to other epidemic frameworks. Other things that I think would be interesting to look at are infection trees. So what kind of genealogies are generated by this process? So here again, here I show you how you can, from these simulations I showed you, reconstruct essentially a colonization path. So what I did here is the original seed was in the center. Then I sampled here equidistantly 100 points and reproduced the colonization path. And that gives you essentially this very nice coalescent tree, and the thickness here represents how many leaves are essentially hanging on that branch. And it really looks tree-like here. And a couple of properties about these trees are understood, like for instance the bushiness, let's call it, where you can describe essentially the transverse width of this tree in terms of the radial distance, radial size of the tree. Their scaling behavior is understood for this kind of dynamics. But then you can ask the question, how does this change when you go into these other regimes? So here I show you reproduce coalescence tree or infection trees for these other scenarios. And I think this would be important because, you have all the sequence data of spreading viral epidemics that are mutating quickly. And in principle, you can imagine sampling these viruses, get DNA and genetic information on genetic diversity, and try to reproduce these trees and then potentially colonization path. And also what's nice about this actually very dumb model is that you get naturally, in a way, hubs, right? You get hubs, individuals that are not in any way special, but still they are crucial for infecting a large portion of the population. There are a number of models or papers that point out, okay, there are people that are representing hubs, and there might be something special about them. But even in these simple models with long-range migration, you can get that. Okay, other things on the horizon, perhaps, is how does hitchhiking work in these regimes? What about soft sweeps when you have multiple mutations occurring in space? What happens when they spread at the same time? That's very well understood by Peter Ralph and Graham Coop when you are in this regime of traveling waves and they merge. But what happens in these other regimes when you grow faster than that, but still not exponential, as in the well-mixed case? What about clonal interference? And what about data? It would really be nice to have an epidemic that that actually can be used to.
So you want to release an infectious agent from the ceiling?
If we could do that in the lab, would also be very nice. With that, let me thank you again, Daniel, for collaboration, and I take questions.
Who's taking questions? Lonnie?
So could you work backwards from the coalescent tree to infer your mu parameter?
So I don't know yet because I haven't worked out the problem. So there's still a question mark there. But I guess because the behaviors of these tree will be pretty different. So how many, leaves, how many, the bushiness more or less of these trees will be very different. I mean, roughly speaking, you might be able to see this here already if you compare these. But I expect to do this, to be able to do this. Not very precisely, but you might be able to say, okay, mu is more in this one regime, first, the second, or the third. You can imagine that.
Is there some relationship between the perpendicular parallel correlation?
Would be nice, I don't know.
It depends on you, or?
I don't have a quick argument for that.
Yes.
So I think you said in your simulations that when you got a jump, it always took off. Is that right?
In the simulation, they are done in this way.
And if I don't want that to happen, do I just thin by 2 times the selection coefficients? Is that how
That would be one way of doing that. But essentially what we have in our dispersal kernel is essentially the product of the two things. Right? So, which makes it faster. So if you would always jump and then not do anything with the jump, that would slow down.
Could you, instead of long-range interaction kernel, use stochasticity, which has heavy tail, like Levy flights, combined directly with the FKPP equation? Would that be analogous? Would you get the same escape?
So you want to combine what? Sorry, the FKPP?
The diffusion, the FKPP equation, and put in, instead of
White
randomness
noise,
that
you
you
wanna
described
put
at
in.
the beginning, something with heavier tails, distribution which has heavier tails.
Instead of the noise.
Yeah, the noise which has heavy tail.
I don't think that this will.
No, that's
do this.
just individuals
Yeah.
having lots of offspring. It's
Right.
got nothing to do with the spatial motion. Because the noise there has to do with
Yeah.
the family sizes
Right.
of individuals, not the movement. So
I just want to make a couple comments. One was just that, I think you said it, but I maybe emphasize again. It's a little surprising, this model, because in the limit that the dispersal is very long, then it's essentially deterministic. We just a little bit of stochasticity at the beginning. In the limit that it's very short range, it's basically deterministic with a little stochasticity around the edge as the pancake is growing. But in the intermediate regime, it's very strongly stochastic, and there's nothing deterministic about it. So it sort of has this rather strange behavior. The other comment I want to make in connection with making contact with the mathematics. So Oskar mentioned that Chatterjee and Day had some results on the, most recently some results on the asymptotic behavior. So we have the detailed outlines of the proof, which covers all of the crossover regime as well as the asymptotic behavior, and has very tight bounds on these forms. I mean, doing this either the log squared regime, when it's something like log squared plus correction with log over log with the coefficient upper lower bounds and so on. And so there's a lot that one can do, sort of making this heuristic arguments, rigorous.
Yeah, that would be nice, because I mean, Chatterjee and Day have very crude results in various regimes, so it takes a long time. He's my student, so I can make fun of him. Not Dave.
Dave's my student.
So they're trying to push through some of these intermediate regimes as well. They do it by rather different ways.
Other questions? Let's thank both speakers and